Okay, so we're going to work on another example of a statically indeterminate problem, axially loaded. So I have a slightly more complicated truss here. So we have a rigid bar, A, B, C, D, which is being supported by the pin supported A, but then it's connected to a steel strut at B and a bronze strut at C. And of course, there's a weight of 50 kilonewtons being hung from it at point D. And what we want to know is we want to figure out what the various stress levels are in the steel and bronze rods. And when we look at this, it's going to very quickly become apparent that we have more reactions or possible reaction forces than we have equations of static equilibrium, and so it's going to be statically indeterminate. Now, up until now, we've looked at a fairly simple, straightforward load applied to a bar, an axial bar, and so this is just to demonstrate how things can gain in some geometric complexity, but the process, if you will, or the method of determining a compatibility equation is more or less fundamentally the same. And so that's exactly what we have to do is we have to figure out a compatibility equation. So I've gone ahead and I've prepared ourselves to draw out a free body diagram. And in this case, I'm looking specifically at the rigid bar ABCD. And so now I need to put my forces on it. So we have two reactions at A. So reaction AY, reaction AX. We have a couple internal forces. I'll draw them pulling on the bar, which is to say that the bar is pulling on them. So tension in the bar. So I'll draw those in tension because that will suit our sign convention we've used. So we have the load in the steel. We have the load in the bronze at B and C respectively. And then we have our externally applied force applied at D, and we know that that's equal to 50 kilonewtons. So we have our three equations of static equilibrium, some of the forces in the x, some of the forces in the y, and some of the moments, but we have four possible unknowns, Rex, Ray, P sub s, and P sub b. So let's look at the geometry and see if we can't draw a relationship between any of these based on the deflections, which is where our compatibility equation comes into it. So I'm going to draw out in grossly exaggerated form the deflection. So the bar is rigid, so it's going to not bend and basically deflect down. And if I were to identify, so this distance in here is our elongation in the steel, and this distance in here is our elongation in the bronze rod. And clearly they are related through the geometry of the problem. I'm going to further identify that angle in there as theta, so we can use that to refer to it, and see if we can't relate P sub s and P sub b to each other through their deflections, delta s and delta b. I'm going to wander up here. I'm going to say derive compatibility. And using small angle approximations and everything else, we know that theta multiplied by the distance, in this case, say 600 millimeters, will give you the value of the deflection in the steel rod. We also know that theta multiplied by 1600 millimeters, which is the distance between A and C, will give us the deflection in the bronze rod. And clearly thetas have to be the same or equal. So if we isolate on theta, that gets us delta S over 600 millimeters and delta bronze over 1600 millimeters, and those are both equal to theta, so they have to be equal to each other. Now recall, we also know that our deflection, axial deflection, is equal to the internal force multiplied by the length over which it acts, divided by the modulus of the material and the cross-sectional area of the material. So we can substitute that in both cases. So we have 1 over 600 millimeters multiplied by the internal force in the steel rod times the length of the steel rod divided by modulus of steel and the area of the steel rod. 1 over 1600 millimeters multiplied by the internal force in the bronze times the length of the bronze rod divided by the modulus of bronze and the area, or the cross-sectional area, of the bronze rod. So now we have most of these parameters are provided to us in the problem. So let's go ahead and substitute this in. So the only thing we don't have are the loads. So we have P sub S times the length of the steel, which is 1,000 millimeters, all divided by, we have 600 millimeters times our modulus for the steel, which we know is 200,000 newtons per millimeter squared, or megapascals, and the cross-sectional area of the steel, which is 600 millimeters squared. And that would be equal to P sub B times the length of the bronze. Length of the bronze is 2 meters, or 2,000 millimeters. And that's all divided by, we have the 1600 millimeters, the E of the bronze, which is 83,000 MPa, or newtons per millimeter squared. And the area of the bronze, which, contrary to what was typed in there, is actually 300 millimeters squared. And that gives us a ratio of our internal, or our force in the steel is equal to 3.61 times the force in the bronze. And we can label that and call that equation 1, if we will, because we'll have to use that for substituting later. So that is our compatibility equation. That gives us that extra thing or item that we need in order to be able to resolve our forces. So now we can basically bounce to static equilibrium. So we're just going to do the sum of the moments about A. So we'll sum of the moments about A. We'll choose clockwise as positive, set that equal to 0, and then we're ready to go ahead. So in this case, we have our force in the steel. It's trying to turn it counterclockwise, so we'll go negative P sub S times its perpendicular distance of 600 millimeters and minus P sub B times its perpendicular distance of 1600 millimeters, and then the 50 kilonewton force going clockwise or positive, so 50,000 newtons, and its perpendicular distance of 2,400 millimeters. Now I'm going to call that equation 2, and I'm just going to go right ahead and I'm going to substitute equation 1 into equation 2 by replacing P sub S with 3.61 P sub B. And now I have simply one unknown, and we can calculate piece of B, or our force in the bronze, to be 31,864 newtons, or 31.9 kilonewtons. Now it's a easy path just to use equation 1, where we can use P sub S is equal to 3.61 times P sub B, which is equal to 3.61 times 31,864 newtons. So we can calculate P sub S to be 115,200 newtons, or 115.2 kilonewtons. So now the problem says to compute and evaluate the stress in each of the rods. So let's look at the two rods then. Determine stress. And we have stress in the steel is equal to the force in the steel divided by the area of the steel. And so in this case, we have our 31,864 newtons divided by our 600 millimeters squared, which gives us a stress of 192 newtons per millimeter squared, which is to say megapascals. And we'll go ahead and we'll do stress in the bronze equal to the load in the bronze divided by the area of the bronze. And so that's 115,200 newtons divided by 300 millimeters squared, or 106 megapascals. Now it's a quick comparison to look at those and to compare them back to the material properties. So if we look at the steel, up in the question it said that the yield capacity of the steel was 240 megapascals. So we're certainly below that at 192. So that's less than the yield capacity of the steel. And when we look at the bronze, we have 106, which is also below 140, or the yield stress of the steel. So that's okay as well, because it is less than the yield capacity of the bronze. And so that's it. So the secret here is, again, to derive a compatibility equation based on the displacements, which then allows you to relate your unknown forces. And so in doing that, through the geometry of the displacements, we were able to resolve for the reactions in the steel and the bronze, and obviously we could apply the other equations of static equilibrium to get the reaction at A in the X and the reaction at A in the Y. So that's it. Again, just a slight different twist on the problem to show, again, how we apply the concept of compatibility of displacements to solve a statically indeterminate problem. So I think that's it for our basic examples for axial load. We're off to do some torsion for a while. We're going to have some review problems, more interesting, more complicated problems. We're going to get there really during the review problems.